Okay, before we can get started, just a small public health announcement. If any of you are not feeling well, have a cold, I know it sounds very unfair to say, I traveled all this way, got into visa issues, show up at the conference, do I really need to sit it out? But in the interest of your own health and of those around you, if you're not feeling well, please do take the time to recover. And for those of you who are feeling healthy, keep the masks on when you're around folks. Okay, with that, let me introduce our next speaker. Absolutely no stranger to all of us who've been at KDD over the years, Dr. George Karypis. He is a distinguished McKnight University professor at the University of Minnesota Twin Cities, and now an Amazon scholar and senior principal scientist at Amazon Web Services, which is AWS as well. His research interests spans the areas of data mining, high-performance computing, information retrieval, collaborative filtering, bioinformatics, chemoinformatics, and scientific computing. His group has published several pieces of software over the years. I, for one, as a new grad student, have used Metis, and that's thanks to George's work at his lab. He has published over 250 papers on all of these topics and 2 books, Introduction to Protein Structure Prediction, Methods and Algorithms, and Introduction to Parallel Computing. In addition, he is serving on the program committees of many conferences and workshops on these topics, and he's on the editorial boards of the IEEE Transactions on Knowledge and Data Engineering, ACM Transactions on Knowledge Discovery from Data, Data Mining and Knowledge Discovery, Social Network Analysis, to name a few. At Amazon, his team works on areas such as large-scale distributed training of deep learning models, model compression, NLP, graph neural networks, multimodal representation learning, and multitask learning. We are thrilled to have him give the second ADS talk. Please welcome George Karypis.
Thank you very much. Still it's morning. Good morning, everybody. So a couple confessions, right? I was trying, I was asked to give a talk, I said yes, right? And then people were asking, okay, what is the title and the abstract of your talk? What's the title and the abstract of your talk, right? So I was struggling to find out, to decide what to talk about, right? So, and the reason for that, because I was giving another talk at the Deep Learning Day, and I wanted to make sure that I minimize the overlap, right? So I think there would be an overlap, but I minimize the overlap. So anyway, so after long and thinking through the process, I decided to talk about not necessarily the work that my immediate groups are doing, but also the work some of the peer teams within my org are doing, right? So let me give you a little bit of a context, right? So I'm part of an org within AWS AI that we call ourselves AI Research and Education, right? So, and for those who are from Amazon, and AWS may know what that thing means, but the education part has to do because our org runs a machine learning university, which is an internal university within Amazon, right? And the research part is because we do a lot of we have some small labs that do a lot forward-looking research, right? And one of the things that we do a lot in that, both on the forward-looking research as well as on the education side, is we're actually making sure that whatever we discover, right, is published, right, and is made available in the form of, ready-to-use tools, for other people to use. So we're very much, strong believers in open source software and tools, right? And I decided to talk about some of that work, right, that we're doing along that front, right? So, so what I will talk about, assuming that I have enough time, talk about 4 things. So the first one is an effort that we started recently called PyY. People are very creative with logos, right? So the second one is I will talk something about AutoGluon, which is an AutoML tool, and many of you guys may already know about it. Then I will talk about DGL, which that's the overlap part that I said about some of my earlier talks today, which is a library for graph machine learning. And then the last part, assuming that I have time, I'll talk about something that we recently developed, and we actually are in the process of open sourcing, so it's not open source yet, but hopefully, that will happen pretty soon. It's called, mics, okay? So, by the way, another, factoid. So, okay, good, so you guys can see that. So we're spending a lot of time trying to design a logo for AI, AI research and education, right? And we wanted to have a logo that will cover AI, research, and education, right? So that logo covers all three things. Can you guys figure out which elements of the logo map to which one of them? So the brain is AI, right? So the graduation cap is education, right? But how about the research? Huh? The magnifying glass, very good, very good. So all the elements, right, of the name of the org are captured in the logo, right? It's the important stuff. Okay, so without ado, so let's start talking about PyY, right? So, so PyY is an open source ecosystem for causal machine learning. So this is something that, you know, so let me give you a little bit of a context before I get to the punchline, right? So we have a research lab in Tübingen, Germany, right? It's very closely affiliated with the Max Planck Institute. And the scientists over there for the last several years have been working on causal reasoning based on graphical causal models, right? So the team has been working on the topic for several years and have developed a lot of tools, and a lot of those tools are used internally, right, by different research groups as well as product groups. Right. So and in the spirit of fostering open source research in that area, we decided to actually open source that effort, right? And we got approvals, from the VPs and SVPs to go ahead and do that, right? So while we're thinking of how to do that, then there is a parallel effort, right, that started from some researchers in Microsoft called DoY, which is another open source library, right, that has to do with causal machine learning. So instead of creating our own open source library and essentially to some extent competing with UI, right, we reached out to Microsoft team, right, and said should we partner, right, and come up with something larger than just either one of those two efforts in isolation, right, and that's what created the PyY effort. So PyY, right, is a joint effort between Microsoft and Amazon. And the idea is to create, an ecosystem, right, around open source tools, right, to foster research in causal machine learning, right? So it was created about, 3 months or so ago, because this is when we announced, right? And it's been created as an independent, GitHub organization, right, in which it has both, members from Microsoft, Amazon, my team, as well as, some external participants. Okay. Now, with PyY, it's a larger effort than just a single library, right? So it's kind of, it's trying to foster the integration of a lot of research around, causal machine learning. So one component of PyY is a DoY, right? So which is a library that initially started by Microsoft. And what we end up doing, we end up actually contributing to that library, right? So if you actually go look at the GitHub, code changes, right? About, 3 months ago, there was pretty much I think it was a 60% increase in the number of lines of code, right, in the library, right? So this is kind of for the history, right, in terms of what is PyY, how it's created, right? And it's actually just a great example, right, in which, scientists and research teams at different companies, right, which, under normal circumstances, would be more on the competitor side, right, and they collaborate together, right, to foster open source, open source research. So that thing as a context and as the story, right? So we'd like to talk about some of the stuff we've been doing within the context of DoY, right? And so DoY is a Python library for various causal inference tasks, right? In terms of stats, right? So it has about 5,000 GitHub starts. And then actually the interesting thing is since we joined forces, that number has increased by roughly about 1.2K, right? And right now has become the most popular, right? Library on GitHub related to causal machine learning. Okay, so what I would like to go through is some of the new features that the AWS has contributed to the DoY library. Right? And the list is not going to be exhaustive, but I'm just going to try to cover, a few of those, contributions and the capabilities, right? So, very good. So the first is a feature that allows to identify and attribute, root causes in complex systems, such as in a microservice architecture that's shown over here. right? So solving such problems manually, it's hard and very time-consuming, right? And having tools to automate that process is a great, be of great advantage, right? Think of an organization like, AWS, right? Having a microservice architecture, and all of a sudden, something is not working and trying to figure out why, right? And this is really what the root cause, analysis system is trying to do, right? So for example, in the case of that microservice architecture, right, what we'd like to be able to do is train a root cause analysis model, right, and then use that thing to explain, for example, why there's a high latency in one of the components, of that system, right? So another capability that we added into the 2Y library is a feature that is designed to attribute distribution changes, right, to the variables in the system, right? So imagine a supply chain where we observe that the number of fulfilled orders, right, in the current week suddenly dropped when compared to the previous week, right? And the natural question to ask, why, right? So with this particular feature, right, it will be able to attribute that distribution change, right, to some of the other variables in the system, right, so they can potentially take action, okay? And which, by the way, that kind of also hints to some of the internal use cases of those tools. So, so another capability that we added to the library is a new measure, right, of quantifying causal influence, right? And that measure is based on the concept of intrinsic contribution, right? So the idea here is the following, right? So think of like a train station, right, in which trains come and go, right? And there are dependencies between the trains, right? So the particular train can only go if another train has arrived, right? So the part that you're trying to understand, how much of a delay, right, can be attributed to a particular train, right, and not was a result of something that was cumulative over the dependencies in that system, right? So this is the whole notion of the intrinsic attribution to a particular event or a particular variable, right? To the quantity that you're measuring, right? And then the next fixture that you can do by the capability that we have to do Y is to do essentially a kind of a what-if analysis, right? So you're trying to figure out to interventions and counterfactuals, right? For example, you can now ask the counterfactual questions whether we will have avoided a peak latency in a particular user request on a website if we have assigned more compute power to the caching service, right? So, and then you can actually ask that question and get an answer, okay? So those are some of the capabilities, right, that, the causal machine learning tools that we incorporate into DoY, right, allow people to actually do, right? Now, the underlying theory behind those things, right, we rely on, causal structural modeling, right, it's, Pearl's, theory, right? And the requirement to use all of those things, right, you need to be able to provide us input a causal graph, right? So that causal graph can be devised based on domain knowledge, right? Or you can use some computational techniques to infer that causal graph under certain scenarios. Okay, so the key thing that I want to stress, and I'm not going to go into the math for any of that stuff, right? Because this is a keynote talk, right? And it's not a depth talk, right? So there's actually a lot of science behind the work within the context of the causal machine learning work that we're doing over here, right? So and this is actually work that goes back more than 10 years ago, right? And actually, there was an interesting kind of factoid as I was putting together the slide. I remembered that not too long ago, right? So one of the work that was done by some of the scientists in the lab over there, right? And you guys can recognize, I'm sure, some of the people in that picture, right? So they actually got the honorable mention, right, for the test of time award at ICML this year, right? So this is actually, there's a lot of science behind the techniques, right, that have been incorporated into DY and PyY. So So we continue to work on that. So this is not like a one point in time type of work. I mean, the team in Tübingen, they are very much, working in that area. And they're driving both the science on the causal machine learning and also there are people over there that they're actively contributing to PyY and DoY, right? And one of the interesting things, or the good thing that happened, right, since PyY was created, right? So in addition to having, two research teams, right, one from Microsoft and one from AWS, working on the problem, there will be a lot of interest from other contributors, right, to join that effort, right? And that, and this is actually very positive, right, to see a community is being created, right, around, causal machine learning. Okay? So, so switching gears, right, I would like to talk about AutoGluon, right, which is an easy-to-use, high-performance AutoML, toolkit, right? And by high performance here means in the two dimensions of performance that I care about, both quality and runtime, right? So, so many of you guys know the standard machine learning journey, right? So you bring the data, right? Then, you train a bunch of models, right? And then, you train a bunch of models. And then what you do is, you use those models to make predictions. Okay? We're in a data mining conference, right? And people will say that the first part of that counts for, 95+% of the time, right? I will not disagree with that, right? But the last two parts of that, right, require a non-trivial amount of science engineering effort, right, to actually make it work, right? I mean, the previous talk we heard, we saw a lot of, science work, right, in trying to actually build high-quality models and do that in such a way that I can actually do inference, right, within my latency bounds, okay? So, and the whole premise of AutoML tools, right, is to eliminate the high science and the high engineering cost. I don't know, that's a goal. The goal is to make the thing go away. Don't do anything on the data side, right? You still have to go figure out the right data, right? But assuming that you have that done, right, then the rest of the stuff, should be just press a button, right? And this is kind of, the idea behind AutoGluon, right? So it's a AutoML tool, right, that is multimodal by its nature, and it can train models, right, based on, tabular data, text data, and image data. Okay? So it's an open source tool. It's very easy to use. I mean, it's the whole idea of, load data, call the fit function, compute predictions, right? It's a 3-line journey, right? And everything else is done by the system, right? And you can do the thing both for standard tabular data as well as you can do the thing for multimodal data. Okay? So I'd like to quickly highlight some of AutoGluon's key components, right, that actually make it to achieve the performance that you can achieve, right? And by the way, there was an AutoGluon tutorial, I think, on Monday, and I don't know how many of you guys were there, but in case you missed it, I'm sure the slides are available for you guys to download from the tutorial to see what's going on. So, so there are, at the high level, there are 4 elements, right, that make AutoGluon, successful, right? One has to do with bagging, the second has to do with assembling, the third one has to do with stacking, and the fourth one has to do with fusion. I could not find a better picture than that fusion. This is very violent fusion picture. Plus, right, a lot of smart engineering and performance optimizations, right? And speaking of smart, right, a little factoid, right? So AutoGluon was started, several years ago, not from our org, but from the consumer side of Amazon, right? And actually, there was a team of engineers. They developed an AutoML tool to win a competition. Competition always inspires, people and brings the best in them, right? So, and this is Alex and Nick. Now the factoid is Nick. I don't know if this Nick is in the audience or not, right? He's a University of Minnesota graduate, right? So that joined Amazon in Seattle, right? So smart engineers, right? To actually build that stuff. Okay. So anyway, factoid aside. So let me quickly talk to you guys about bagging, right? Versus hyperparameter search, right? So usually when we're trying to train a model, right, what we do is we pick up one or two kind of, model types, right? And then we do a sweep over a bunch of hyperparameters, right? We rely on some sort of a cross-validation to estimate performance, right? Then figure out the right hyperparameters, right? And then we train our final models using that, right? So all the compute we did up to that point, we just throw it away, right? All the models we have trained up to that point, we just throw them away, right? And we just, the only output of that exercise is a set of hyperparameters, right? So AutoGluon does not do that, right? What AutoGluon does is relies on bagging, right? To actually leverage all those models to train a bunch of different models, right? And use all of those models to do predictions, right? I mean, it does some limited hyperparameter search, but it's not the hyperparameter search, right, that actually drives the quality, right? It's the fact that all the CPU or GPU cycles that they spent to train all those models, right, that they actually contribute something, right, to the prediction. Because that's one component. The second part is the notion of ensembling, right? And I'm sorry, let me quickly go through my animation here. And the idea here is that, I mean, all of us are researchers, right? So we have our favorite model, and there's always a data set in which our favorite model does not perform well, right? And someone else's model, or even something very simple, performs well, right? So to essentially guard against that, right? The idea of AutoGluon is to just use ensembles, right? So use a variety of different models, right? We train them, right, in the bagging setting, right? And we use them to compute predictions, right? So now the third component is that those models, the output of those models get stacked into multiple layers, right? So I have my input features, train a bunch of models, right, using bagging, get a bunch of predictions. Those predictions become inputs to a second thing of doing the same thing again along with the input features, right? And that process can continue, right? As many layers as you want, right? So this is the notion of a multi-layer stacking, right? And the fourth component, right, has to do with the fusion that I mentioned, right? It's designed to address the fact that most of our ML problems nowadays are not just tabular ML problems, right? They are multimodal models, right? So this is a typical problem that Amazon catalog faces, right? I have an image, I have some description of what is a product, I have another image, and I'm trying to ask the questions, are those two things the same product, right? So F of data, the data contains tabular data, right? We have a bunch of categorical things, contains text, right? A description of title, and so forth, and contains images, right? And what we like to be able to do is we like to be able to enable our AutoML, toolkits, right? To effectively take all that information into account, when they train those models, okay? So, and so the fusion and combination component, right? There are actually a couple capabilities over there. So one has to do with, how to fuse the different modalities together, and there's a bunch of approaches that has been, incorporated into the tools, right? And the second part is, how to combine some of the foundation models, right, with some of the more traditional tabular models together, right? Within the framework of bagging, ensembling and, multi-stack, multi-layer stacking, right? So, and those pictures over here talk about text and tabular, right? But, recently the AutoGluon 0.5 version has been released that actually allows you to incorporate, images as well, right? So essentially capture, the three dominant modalities, right? And there's work in progress to include my favorite type of input data, which is graphs, right, in that process as well, okay? So AutoGluon, has been evaluated, extensively, I guess. I mean, so the AutoML community has a lot of competitions, and it's great, right, because at the end of the day, it's supposed to be like a push a button, get results. So it's very much amenable to those automated evaluations, right? And you can see that, in recent years, right, across, different, competitions, AutoGluon, it's really, close to the top, if not the top performing method out there, right? And this, again, this is an open source tool. And there was an instant evaluation that computed some sort of a Pareto frontier of all the AutoML tools, right? And there are different points over here associated with AutoGluon, and the difference across those points is, what is the budget that you set for inference cost, right? So which is a surrogate, right, of the complexity of the model that you're actually training, right? So we're not looking at the training time over here as the variable of interest, but the inference time, right? And you can see that, different trade-offs between, accuracy and inference time, right? AutoGluon is really at the Pareto frontier across, different set of tools out there. Okay? So anyway, so this is an effort that has been going on, Nick and Alex started on that thing, 2018, some time ago. But I think the efforts of the open sourcing of that, right, and the very much active development and the creation of a community around it is about, close to a couple of years effort, right? And this is something that is, very much actively, evolving, right, both on the science as well as, the capabilities of the tool. Okay. So, okay, I'm doing good with time. So then I can spend as much time as I want on my third topic. So the third part I would like to talk, right, is DGL. DGL stands for Deep Graph Library. So this is a framework for developing, training, and using graph neural networks. Okay? So if I was in a different conference at a different, maybe 3 years ago, I will say that none of you guys have heard graph neural networks, but we are in 2022 in the KDD, and I'm pretty sure everybody knows about graph neural networks, right? And I realized that the 3 awardees for the doctoral dissertation awards that I was sharing this year, all 3 of them had to do about graph neural networks. And that was not by design, right? So it just so happened that a lot of the work in recent years has to do around graph neural networks, right? So graph neural networks is a family of deep neural networks that are designed to learn deep representations of nodes, edges, and graphs, right? And they are used, this type of machine learning models, are used to solve problems like, node classification tasks for like identifying fraud, link prediction tasks for like a recommendation or a knowledge graph completion, or tasks associated with classifying an entire graph, like, predicting whether or not a particular, small molecule, right, represented by its graph, will bind to a particular protein, right? And by the way, that protein itself can also be represented by a graph, right? So it's going to be a link prediction of graphs, so to speak, right? It's a very interesting problem. Okay, so GNNs is a very active area of research. It's a very dated, keyword hotness chart, right? But it's something that there's a lot of work in that area. Okay, so DGL, right, is an open source framework, right, whose development started back in 2018, right? And they initially was a collaboration between NYU and NYU Shanghai, right? So that was initially started outside the AWS, realm, so to speak, right? But the people involved in DGL, joined, the AWS, research lab that we have in Shanghai, and they brought a lot of that activity inside the lab. Right, and since then, AWS has been one of the, I would say, primary developer and contributor to that effort, but not the only one, right? Especially the last, year or so, there has been a lot of contributions from actually, colleagues from NVIDIA and Intel, as well as some other big companies to optimize, DGL for their own workloads. Okay, so it's a framework that is, I make the statement, it's a more favorable framework by academic and industrial users, right? And this is something that I based on some data that NVIDIA shared with me. Unfortunately, I cannot tell you what is the data, but you guys have to take my word for that. So what makes DGL stand out can be summarized like 4 features, right? Number one is it's designed to be easy to use, right? and offers a very extensive API, right? And different types of API, and I can get, I think, the next slide, that makes it easy, for people with different levels of expertise, to develop GNN models and train them and use them, right? By the way, my meaning of the term use is to actually do inference on those at scale. Okay? So it's efficient, right? It has a lot of system-level optimizations, to actually get, as much flops, right, out of your hardware as possible, right? It's scalable, right? It can scale to extremely large graphs and large systems, right? And by large system here, I'm talking both a single node, multiple GPUs, as well as a distributed multi-GPU cluster, DGL can support, right? And there's actually a large ecosystem of software, right, that builds on top of DGLs and provide a lot of, domain-specific capabilities to both scientists as well as applications. So DGL is it's not a small code base, let's put it that way. So it's designed to address the needs of different types of users, right? Both from the researcher, like the graduate students or a postdoc, they're doing research, right? And they're starting to learn, GNNs. The data scientist, right? That wants to take advantage of GNNs, without, diving very deep into the actually coming up with new models, right? As well as the people who care about performance, right? The people that actually, they have to deploy a GNN model, right, that was created by applied scientists, right? And they need to be able to meet, performance requirements in terms of, training speed as well as inference speed, right? And in order to do that, it has it provides both APIs that cover different components, like for instance, standard message passing computations, dealing with heterogeneous graphs, doing graph sampling for scalability, different data utilities, distributed training, and so forth, right? So those are the types of functionality that it provides, right? But also they have the APIs in terms of the high-level API in which, I just want to run stuff, express something without necessarily knowing anything about what's going on. Something that is more geared towards like someone that is familiar with PyTorch, right? So they can, familiar with that particular style of programming. And then the people like, old people like me that like to program in CUDA every now and then, right? They want to actually get performance, okay? So to be actually go down and actually implement that stuff, okay? So this is at a high level what DGL provides, right? And so one of the, in addition to the API though, so one of the things that we introduced, not too long ago is a command line interface to all the GNNs and GNN capabilities, right, that DGL provides as a library, right? So in this particular, case, what will happen is I can have a user, right? Just execute a command like a DGL configure node-pred, right? And provide some parameters, right? So through a command line interface, right, that's seen to be a web interface, right? They'll be able to select the task, right? Select the model, right, that they want to train, right? And potentially select one of the built-in data sets, right? Or provide their own data set, right? And by doing that, what is happening is that a configuration file gets created, right? And then that configuration file, then the users can potentially tweak that configuration if they want to, right? And then they can just execute a command that says, DGL train, right? It will read everything from that configuration file and actually train a model, right? And then that model can then be used to actually do the inference, right? They can bring their own data, right? And then a data scientist can actually, go ahead and execute, apply that model on the new data, right? At the same time, what they can do is if they want to use, they can use a command called DGL export, which what the thing will do, it will actually generate DGL Python code for what it just did, right? And that can be kind of the starting code that someone can start modifying, right? To modify the model, right? Or to modify some aspects of that, right? Think in terms of like a code generator, right? for a particular task, a particular starting model, that can kind of, bootstrap the whole process of actually, customizing those things, right? So this is something that, was released recently. We're very much actively, developing it, right? And any feedback that you guys can provide about, the DGL Go kind of capabilities and, the type of functionality you'd like to see, feel free to share them with us, right? So, I mean, so DGL kind of give you like a history chart, right? So as I mentioned, it started, sometime in 2018. The first, public release was done during NERS, 2018, right? And since then, it has been, the development has been very active, right? As I mentioned to you, the teams that they're working on that is actually a team primarily in Shanghai lab, as well as in the lab that we have in Santa Clara, that they're working and developing DGL, right? And by developing DGL, really what I mean here is that they're doing research on some of the underlying components that feed into DGL, right? And this is both a systems level research, right, as well as modeling level research, right, to enable, right, the training, right, of effective large GNN models, right? So just to give you an idea about some of that nature of that research, right, and if you guys were on the deep learning day, you probably have heard me talk about that, is that, as I mentioned to you, DGL provides different types of APIs, right? There's an API that relies on user-defined functions, UDFs, right? That it's very easy to understand. It actually mimics the math, right? So usually on a GNN, what I have, a mathematical expression of the model that I want to train, right? Then if I'm going to be using, and most of those models, rely on a message passing framework, right? So then you write code for your message functions, right? And then nicely maps your math to the code, right? Unfortunately, if you run that thing, it will not run very fast, right? Because, so that's why DGL provides another API that is geared for the gearheads, so to speak, right? The people that want to get high performance, right? And they can use that API, they can get high performance. And again, this is not an eye test, right? But that API maps very closely to CUDA primitives, right? So people can actually map the computation to something that we know we can compute very efficiently, right? Using, the optimized libraries that NVIDIA has provided. Okay, so there's a usability and easy to understand gap, right, between those two things, and there's the associated performance gap, right? One code can be up to 100 times faster than the other code, right? So one part of the research that we're doing within the DGL team is trying to actually bridge that gap, right? And this is, we have a project that a lot of the insights from the project, making back into the DGL on actually defining, a graph filer, which is a compiler for GNNs, right, for message passing data flow graphs. The idea is to essentially, analyze and extract the message passing data flow graph, perform a bunch of transformations, right, on the data flow graph and optimizations, right, and generate optimized code, right, so that we can achieve exactly the same performance that you get with your hand-tuned code compared to your high-level kind of, UDF-based code, right? And we actually did some experiments, and don't have time to go to any details, but the key thing over here is the last bar is a graph filer. Everything up to here are hand-optimized versions. That thing here is a UDF, right? And as you can see over here, the compiler's output, right, in most cases matches, and in some cases actually outperforms, right, the hand-optimized, implementations that we have, right? And it's considerably faster, right, than the UDF-based, implementation. Okay. Another example of research, right, that goes into DGL is the work we have been doing for the last year and a half or so on actually scaled GNN training to very large graphs using a distributed mini batch-based training approaches, right? And then plugin for the other talk that I'll be giving tomorrow, we're actually presenting that paper that actually describes distributed DGL, right? That is the latest work in that area. That actually it's a distributed training of very large graphs on a cluster of multi-GPU machines, right? In which, we take advantage the GPUs across the cluster as well as the CPUs across the cluster. Okay? So the thing that I mentioned is that, DGL is not just one library, but it's actually, there is quickly an ecosystem that's been formed around DGL, right? We have a bunch of packages dealing with knowledge graphs, different scientists, developing visualization capabilities on top of DGL. There's an effort on open heterogeneous graph neural networks that relies on DGL to develop capability for very complex, GNNs. There are benchmarking capabilities that utilize DGL. Many graph database providers, right? They're providing graph machine learning capabilities, right? And they do the thing, using DGL, including AWS as well as Neo4j, TigerGraph and ArangoDB. There's the NLP, GNN-based packages for NLP that build on top of DGL, and there are a lot of life sciences-related packages, right, that also build on top of DGL, right? So there's an ecosystem that has been created, right, of domain-specific open source packages, right? Or at least most of them are open source packages, right? That that build on top of DGL. So as I said, it's a vibrant open source effort, right? All the metrics are high in terms of starts, forks and so forth, right? And the part that I really like about that, right, is not really driven entirely. I mean, AWS at this point in time is really a small component, right, of the number of people that are actually contributing to that effort, right? So, the last time I checked, there are 229 contributors, right, on the GitHub, out of which I know that the AWS people are 11, right? And then as I mentioned, we have very active, collaborations with both Intel and NVIDIA, and, working together to both, define some of, what DGL should look like, and also, the scientists in those teams are actually contributing models and optimizations. Okay? So, and now switching gears to the last part I want to talk about, and the one I want to talk about is about mics. Okay, and this is the subtitle of that is a scaling training of very large models on public clouds, right? So I'm sure all of us are aware of the fact that the transformer models, right, have pretty much taken over, right? A lot of the NLP and CV type of tasks, right? And the size of those models, right? And it keeps on growing. I think it's almost like an arm race, right? Who's going to have the largest and largest model, right? So those models need to be trained, right? And training those models is a compute-intensive exercise, i.e., a very expensive exercise. Okay, so what we want to do is to try to get the most out of the hardware that we have, so that we can reduce both the time and the cost, right, associated with training those models. Okay, so speaking of the hardware that we have, right, so as you guys I'm with AWS, so the hardware that we currently have at AWS, the premier, right, compute instance for this type of workloads is a P4D, right? So the P4D is a node that has 8 A100s, right? Each of them has 40 gigabytes. There's a A4DE instance that has the 80 gigabyte chips, right? And those things are connected via NVIDIA's interconnect within the node, right? And across the nodes, right, they are connected with Amazon's proprietary network called EFA, right? And the bandwidth between two nodes, right, within the machine is 600 gigabytes. The bandwidth across the machine has to go through an EFA that has 400 gigabits per second, right? So make sure that my numbers are correct. Okay, so anyway, there's a lot of bandwidth between the machines, right? But there's more bandwidth within the machines, right? So, and people who come in from high performance computing, I said that's okay. Always your interconnection network across is smaller than your interconnection network within, right? So now in terms of parallelizing those workloads, right, there are two prototypical ways of doing that. One is called the data parallel, the other one is called the model parallel, right? So in the data parallel way of training those things, what you do is you have each compute unit, and you have to define what a compute unit is kind of own the entire model, right, and perform computations for different chunks of data, right? And you have the model parallel way in which the model, which are the weights, right, of that model, are distributed across, compute units, right? And again, those compute units are usually GPUs, right? And then each GPU does each part of the computation associated with a set of weights that it has, right? And all of them together, processing, let's say, the same mini batch, okay? And when it comes down to model parallel, I have both, a tensor and a pipeline way of doing that and so forth, right? So between those two ways, data parallel is by far the easiest to do, right? Because really what it is your serial code, replicated k times, right? That's really what it is, right? So in model parallel, you actually have to split your computations, right? So, and that actually creates a complexity in terms of actually having to code that. To some extent, you can automate data parallelism, right? You cannot nicely automate, right, model parallelism, okay? So now the drawback with data parallelism, right, is that the model is replicated, the model weights are replicated, right? So that the memory footprint, right, it scales linearly with the number of nodes that you have. So that thing does not scale for very large models, because after a while you're going to run out of memory, okay? So what we have over here, we have data parallel is easy to use, straightforward. Everybody can take advantage of that, right? But it's memory inefficient, right? So we have to do model parallel, right? So to bridge that gap, actually the Microsoft team, right, developed the zero optimizer, right? So and some of you guys may have heard those things, right? So it's incorporated into deep speed, right? So the idea of a zero optimizer actually is a very smart idea. It says, let's do data parallel, right? But instead of replicating the data, let's split the data, model weights or whatever. Let's replicate them, right? And every node, every compute node, whenever it needs something that it doesn't have, we'll just go grab it. Right? So this is at the high level the idea, right? Of course, the go grab it is done in an efficient way and all that stuff, right? And within the context of a zero optimizer, there are like three different stages. One is, you optimize the optimizer state, then by splitting them, then you optimize the gradients by splitting them, and then the last stage is you optimize actually the model parameters by splitting them as well, right? And as a result of that is you have the memory footprint of data parallel, memory footprint of model parallel with the ease of use of data parallel, right? It's the whole idea of having your cake and eating it too, right? So now, one of the drawbacks of that approach, right, is that splitting of that stuff that you see over here is done across the entire machine, okay? And that may be an overkill if your model is not big enough. In other words, if your model cannot fit on one GPU, you have to split it. But you may get away by splitting it across 3 GPUs or 4 GPUs. You don't have to split across, 512 GPUs that you may have in your cluster, right? So this is the whole idea of a model size aware splitting approach, right? It's something that can actually reduce the communication overhead, right? Because when you have to go fetch stuff that I mentioned, right? You fetch it for things nearby as opposed from over across your entire machine, right? So this is the key idea that we took advantage of, right? To develop mics, right? And so Mike's, what he's trying to do is trying to minimize that communication scale, right? Minimize essentially the size of your MPI communicator over which you communicate, right? For those guys who come from an HPC background, okay? So there are 3 components that Mike's incorporates, to actually, optimize the training. So one is what I said, model size-aware model partitioning. So you partition the model, right, based on its size, on the number of GPUs that is required and no more, right? The second part is we take advantage of the heterogeneous network of today's machines, in which the stuff within a node are better connected than stuff across a node, to actually build a set of hierarchical collectives to do the communication, right? And then the other part is we employ what we call a two-hop gradient synchronization, right? In which usually when you do mini-batch processing, you process this mini-batch in micro-batches, right? And instead of doing all your accumulations across your entire set of nodes that you operate, you can kind of stage those accumulations to first be locally through the entire set of micro-batches, and then just do a global communication only once at the end, right? So this is the idea of a two-hop gradient synchronization, right? So we put those things together, and what we're able to achieve, a 2.8 speed up over what the best performing configuration of deep speed can do, right? So that translates to being able to train your models, roughly 3 times cheaper, right? And if training the model will take $10 million, now you take 10 million divided by 3. I mean, that's real money, right? I mean, those are not cheap workloads, okay? And then the other part that is, and again, this is some performance numbers over here, but and the other part is, and by the way, this experiment was done on not on the P4D instances, but on the previous generation instances, and we also did experiments on the P4Ds, right? And we're able to train. The good thing over here is that we're able to achieve, right, over 50% of the peak performance of the GPU. Right? And for those guys who are familiar with that part, right, getting anything over 40% on the GPUs is considered, a tough business. Okay, so this is that actually leads to significant performance improvements by doing that. Right? So as I mentioned, this is something that we're in the process of open sourcing, and we're actually working very closely together with Microsoft. A lot of the optimization we have been doing in the context of deep speed, both my team as well as some scientists from Alexa, which are here. We're pushing all those changes back to the mainline code, right? So that everybody can take advantage of those communications, of those optimizations. Okay, so closing remarks, right? So. By the way, I like taking pictures, and this is a picture that I took, right, while I was hiking in Switzerland. So, so I believe that open source ML tools, have developed the AI revolution, right? I mean, if you think in terms of, what has enabled a large number of people, right, to quickly, right, start using AI, right, and benefiting from AI, right? It's not that all of a sudden the number of smart people has increased dramatically, right? I understand that all of you guys are smart, but I'm pretty sure 10 years ago, the equivalent people in that room should have been equally smart, right? So what has changed, right, is that right now we have the tools that make it easy for us, right, to try out ideas, right? So the delta T from idea to result is tiny. Okay, so and a lot of it has to do with the fact that we have high quality open source tools, right, that have enabled that part, right? So and this is by the way, I mean, the whole notion about open source being the critical component, right? It's not just a soundbite. I truly believe, right, that this is something that is that has enabled, right, us to be where we are today. Okay. Now, but I believe, and right now I'm wearing my university hat, right? I believe when it comes down to the open source, right, it should not stop to tools, right? So one part that needs to be open source, right, is data, right? And because access to the data, right, it actually prevents a lot of scientists, right, for actually making meaningful contributions, right, and actually advancing the field. Okay, and also it's very important to ensure reproducibility, right? It's very hard to compare methods, right, or to actually determine and like advance the state of the art, right? Without being able to do an apples-to-apples comparison between your method and the previous method, okay? And that requires access to the tools, and I think we are there, right? But also we need to require access to the data. Of course, the third part is access to compute, but I won't even get there. But at least data is something that without the data, right? We cannot really continue to innovate in this space. And I'll stop.
Hello. Thank you so much, Dr. Karypis. This is like super awesome session. The work you guys are doing here seems to be in this ML ops area, and then there's a lot of for-profit companies that are playing in the same field. So do you guys see that this work may be like in direct competition of those companies, or maybe even wiping out those companies, or do you see both coexist in this field? Thanks.
Yeah, I mean, this is a very good question. So I think everybody can coexist, right? I mean, one of the things that I have come to appreciate, right? So is one thing is to have the capability in terms of an open source, right? And the other one is to have really the support that comes in from someone, right, providing you a service like that, right? So when it comes down to, I would say, the science behind those tools, right, or the core capabilities, right, I think everything will converge to the same thing. Everything converges, right? It's, the competitive advantage, right, is going to be maybe 3 months, 6 months, maybe a week. I mean, we move very fast, right? So I think where where the room for both open source efforts, right, as well as commercial entities providing services like that, right? It really will come in when it comes down to actually the level of support, that they provide.
Got you. That makes sense. Thanks.
Yep.
Any other questions? So Viv, I had a question. So talking to some of the participants yesterday who had adopted a particular open source framework, but the support has started to come down, but they are working in a company, it's very integrated into their systems, and now they're kind of stuck, right? Because migrating out of that is going to be a big cost. So yeah, let's use Onyx and all of these other sorts of things, but that's not really at the standard of a production system just yet, right? It limits you as well in certain things. So how should, let's say, the small scale players who don't have the ability to develop something in-house be smarter about their choices that they make, or what can they put in to make it more flexible?
Yeah, no, this is a very good question, right? But I think there are a couple dimensions to that, right? Number one, the question is it more risky to take a dependency of an open source versus open source effort versus a closed source effort, right? I will argue the closed source effort is much riskier, right? Because you have no plan B, right? At least in an open source effort, you have a plan B of hiring an engineer to continue developing that, right? That's one comment. But the issue about what people should look, and at least what I look, right? I look at how what is the ecosystem around a tool, right? And how vibrant that ecosystem, the community around it is, right? So if there's a vibrant community, i.e. a lot of people have taken a dependency on that and contributing to it, right? I mean, I would consider to be something like that to be safer, right? Than something that is, simply lacks those things. So, but yeah, when it comes down to risk between open source versus closed source, I'm a true believer that I think, closed source, right, or proprietary solutions are much riskier, right? Because you have no plan B. I mean, you have a plan B to go to a different solution, but it's a much expensive plan B. Yes?
Hey, George, thanks for the presentation. That was a very good breakdown of some of the different frameworks. I have a question about the framework for DGL. There was a section in one of your slides where you have some of the different components with the APIs on the left side of that slide. And one of the components had to do with the graphs being part of DGL. And my question is, are a suite of graph algorithms implemented within DGL, or is the DGL framework tested and verified that it can derive and learn the features that typically a graph algorithm would give you if you run it discretely?
But by graph algorithm, you mean like a graph analytics algorithm, right?
Yeah.
So in the chart over there, there was something in the middle. I noticed that said graph should actually have said dist graph, no DGL graph, but this is just a data structure. But to answer really your question, right? So in principle, right, the message passing framework can be used to implement many graph analytics algorithms, right? Because it's a message passing algorithm, right? It's like a neighborhood pooling, right? I mean, you can do anything in that framework, right? So now question is, can I develop graph machine learning approaches, GNN approaches, right, to predict some of the results of those graph analytics, right? I mean, there has been some work in that area, and people, were training models, for example, to predict the page rank, not compute the page rank, but predict the page rank, right? But DGL, the graph algorithm that it provides are I would say, simple algorithms that they're required to actually write GNN models for. Like, for instance, the algorithm to do some form of a clustering or subgraph extraction, like manipulating the graph, so that you can use those things to actually, express, your sampling algorithm or your computations, right? DGL itself does not do graph analytics. Having said that, there was a tutorial on Monday or Tuesday from the cuGraph team that have actually integrated cuGraph with DGL, in which they can combine, graph analytics, done in cuGraph, right, used as potentially inputs, as additional features to a GNN model trained, using DGL.
Yeah, that makes sense. But the second part of the question is, has DGL been verified that it can, let's say given anywhere between 8 or 32 different algorithms that you can run on your graph, is it designed to learn some of those features in a unsupervised approach?
DGL itself, it's a framework, right? The thing that is learning is the model that you're developing, right? So really the question that you're asking, right, it's not really a DGL question. It's really have there been GNN models, right, that have been shown, right, to be able to learn, right, some of the results coming from the graph analytics algorithm, right? And my answer to that question is, for some of those tasks, there have been, right? For some of the other tasks, I don't know. But this is not a DGL question. This is a question about the GNN's model's ability, right, to actually learn that stuff.
Yeah. I think the part of the question comes from seeing that block diagram around graph algorithms. Okay. Thanks, George.
Yep. Thank you, guys.